Welcome to a journey through the cutting-edge world of robotic manipulation. In this video, we'll explore how deep reinforcement learning is being used to teach robots to handle deformable objects, like cloth, in ways never before possible. This project, conducted at Imperial College London's Department of Computing, aims to bridge the gap between simulation and real-world performance. We'll break down the objectives, challenges, and breakthroughs that make this research a milestone in robotics. Let's dive into the fascinating intersection of machine learning, simulation, and real-world robotics. Most robotic manipulation research has focused on rigid objects. Think blocks or tools that don't change shape. But many real-world tasks involve deformable items like cloth, cables, or even medical sutures. These objects introduce a host of new challenges. Their shapes can change dramatically with even small movements, making them much harder to model and control. For robots to be truly useful in homes, hospitals, and factories, they need to master these tricky, flexible materials. That's why this project zeroes in on teaching robots to fold towels, hang cloth, and more. Additionally, robots have been programmed step by step for each task: find the object, plan a path, grasp, move, and release. This works for rigid items but falls short with deformables, where even tiny errors can lead to unpredictable results. Instead, the new approach uses machine learning to let robots learn directly from sensor data like camera images without hand-coding every step. This end-to-end learning means the robot can adapt to unexpected changes and recover from mistakes, making it far more robust in real-world scenarios. Deep reinforcement learning, RL, is inspired by behavioral psychology. Here, a robot or agent learns to maximize rewards by interacting with its environment. The engineer only needs to define the goal and reward. The robot figures out how to achieve it through trial and error. Deep RL uses neural networks to map sensor data to actions, allowing robots to learn complex tasks like folding towels or draping cloth, even recovering from mistakes along the way. Training robots in the real world is expensive and slow. By using simulation, researchers can run thousands of experiments in parallel, speeding up learning and reducing costs. However, transferring what's learned in simulation to the real world, known as crossing the reality gap, is a major challenge. This project tackles that by using domain randomization, making simulations varied enough that the robot skills transfer smoothly to real hardware. The project sets out three main objectives. First, to build or adapt a simulator that can realistically model both robots and deformable objects like cloth. Second, to select and improve deep reinforcement learning algorithms that can learn manipulation tasks from raw images. Third, to ensure that the skills learned in simulation can be transferred to a real robot, without needing additional real-world training. Each of these steps required innovation and problem-solving at every turn. Finding a simulator that could handle both robots and deformable objects wasn't easy. Many popular engines were either closed-source or lacked features for robotics. After evaluating several options, the team chose Pybullet, an open-source physics engine with experimental support for soft bodies like cloth. But Pybullet wasn't perfect out of the box. It needed significant improvements to support realistic cloth manipulation and stable robot control. To make Pybullet suitable for this project, the team added new features: better cloth creation tools, improved rendering, and more stable grasping mechanics. They also fixed bugs, optimized performance, and contributed their changes back to the open-source community. This groundwork was essential for creating environments where robots could learn to manipulate cloth in ways that would transfer to the real world. With the simulator ready, the next step was to define tasks that would challenge the robot and be relevant to real-world applications. The team focused on three main cloth manipulation tasks: folding a towel up to a mark, folding a piece of cloth diagonally, and draping a towel over a hanger. Each task was carefully designed to be achievable in both simulation and on a real robot, providing a solid testbed for learning and transfer. Choosing the right learning algorithm was critical. The team evaluated several deep reinforcement learning methods, including DDPG and DQN, focusing on those that could handle continuous actions and learn from raw images. They implemented recent improvements from the literature, such as prioritized replay buffers and demonstration learning, to boost performance and stability. To bridge the gap between simulation and reality, the team used domain randomization. This technique introduces random variations in the simulation, like changing colors, lighting, and object positions, so the robot learns to be robust to differences it might encounter in the real world. This was key to achieving successful sim-to-real transfer without additional real-world training. One major challenge was the lack of stable, supported soft-body simulators. Pybullet's soft-body features were experimental and buggy, requiring the team to implement new features, fix memory leaks, and debug segmentation faults. These technical hurdles demanded deep dives into both Python and C++ code, as well as creative problem-solving to keep experiments running smoothly. At the time, there were no standard benchmark tasks for deformable object manipulation. The team had to research and design their own set of feasible, meaningful tasks, then implement custom environments to evaluate the robot's learning. This required balancing realism, difficulty, and the limitations of the simulation engine. Deep RL is notorious for high variance in results and long training times. Experiments could take over 24 hours, and results were often hard to reproduce due to the stochastic nature of both the environments and the algorithms. The team had to carefully manage experiments, track changes, and sometimes deal with failures caused by hardware or software glitches. Transferring learned policies to a real robot brought its own set of challenges. Hardware issues like damaged grippers and software incompatibilities such as outdated SDKs required significant engineering work. The team had to build a robust infrastructure to test policies on the real robot, ensuring reliable and repeatable experiments. A major achievement was extending Pybullet to support realistic cloth simulation. The team added features like strong cloth anchors and fake grasps, enabling the robot to interact with cloth in believable ways. These improvements made it possible to simulate tasks like folding and draping, which are essential for real-world applications. Environments were designed so the robot learned directly from pixel observations, just like a human would see through a camera. This approach avoids hand engineering features and allows the robot to generalize across different tasks and settings. The team combined convolutional neural networks for image processing with fully connected layers for low-dimensional data, creating a powerful learning architecture. Perhaps the most exciting result was showing that policies trained entirely in simulation could be transferred directly to a real robot. By using domain randomization and robust learning algorithms, the team demonstrated successful cloth manipulation on real hardware, without ever using real-world data during training. This is a significant step forward for practical robotics. To understand which features and improvements were most effective, the team performed ablation studies, systematically removing or altering parts of the learning algorithm. This helped identify which changes truly improved performance and which were less critical, guiding future research and development. At the heart of this project are artificial neural networks, computational models inspired by the brain. These networks are trained using backpropagation and gradient descent, allowing them to approximate complex functions from data. Convolutional neural networks, CNNs, are especially powerful for processing images, making them ideal for robotic vision tasks. Reinforcement learning revolves around four key concepts: states, actions, rewards, and observations. The agent robot interacts with its environment, choosing actions to maximize cumulative rewards. The process is often modeled as a Markov decision process, where the next state and reward depend only on the current state and action. Value functions and policies guide the agent's learning and decision-making. Q-learning is a foundational RL algorithm that updates its understanding of the environment after each action. Deep Q networks, DQN, extend this by using neural networks to approximate the Q function, enabling learning in high-dimensional spaces like images. Techniques like experience replay and target networks help stabilize training and improve performance. For tasks with continuous actions, policy gradient methods like DDPG, deep deterministic policy gradient, are more effective. DDPG learns both a policy which action to take and a value function how good that action is, using neural networks for both. It's especially suited for robotic control where precise, smooth actions are required. The team also experimented with other RL algorithms like HER, hindsight experience replay, PPO, proximal policy optimization, and TRPO, trust region policy optimization. While these methods have their strengths, DDPG was ultimately chosen for its suitability to the project's continuous control tasks. For tackling cloth, researchers studied how robots manipulate simpler deformable objects like ropes and cables. Early systems relied on visual feedback or mathematical models to plan and execute tasks like knot tying or cable insertion. These foundational studies highlighted the challenges of high-dimensional, flexible objects and informed the design of more advanced manipulation tasks. Cloth manipulation is even more complex, involving subtasks like grasping, laying, folding, and flattening. Early approaches often use specialized hardware or constrained environments. More recent work focuses on using general-purpose robots and machine learning to identify grasp points, plan folds, and adapt to unpredictable cloth behavior. One effective strategy is to seed learning with demonstrations, examples of successful task execution, either from humans or in simulation. This helps the robot learn faster and more reliably, especially in tasks with sparse rewards or complex dynamics. The project collected demonstration data and simulation to kickstart the robot's learning process. Beyond reinforcement learning, researchers have explored supervised and self-supervised methods for robotic manipulation. Supervised learning requires large labeled datasets, while self-supervised approaches let robots collect their own data through exploration. Both methods have contributed valuable insights, but RL offers greater scalability and adaptability for complex, real-world tasks. Simulation-based learning allows robots to practice thousands of times without risk or expense. By randomizing simulation parameters, robots can learn robust policies that generalize to the real world. This approach is especially valuable for tasks like cloth manipulation, where real-world experimentation is slow and costly. The team compared several simulators, VREP, Blender, and Pybolit, each with its own strengths and weaknesses. Pybolit was chosen for its open-source nature, support for soft bodies, and compatibility with robotic models. However, it required significant customization to meet the project's needs. Key improvements to Pybolit included new APIs for cloth creation, enhanced rendering, and better memory management. The team also addressed issues like unstable grasping, lack of self-collision, and state saving for soft bodies. These technical advances enabled more realistic and stable simulations for learning. Test and benchmark learning algorithms. The team implemented a range of environments, from simple 2D tasks like cartpull and pendulum to complex 3D manipulation with both rigid and deformable objects. These environments provided a progression of challenges, allowing for systematic evaluation and improvement of learning methods. The core of the project focused on three 3D cloth manipulation tasks: diagonal folding, folding up to a tape, and draping over a hanger. Each environment was carefully crafted to be both challenging and achievable, with randomized initial conditions to encourage robust learning and generalization. Designing effective reward functions was a challenge in itself. Agents often found clever ways to exploit poorly defined rewards, such as crumpling cloth or throwing it in the air to achieve success criteria. Through careful iteration and testing, the team refined rewards to encourage genuine task completion rather than shortcuts. The team evaluated simulation quality in terms of deformable object realism, stability, and performance. While some limitations remained, like lack of self-collision and perfect deformation stability, the improvements made Pibolet suitable for meaningful learning and transfer experiments. Learning performance was measured by success rates in simulation, variance across runs, and the ability to generalize to new conditions. The team also analyzed learning curves and conducted ablation studies to understand the impact of different algorithmic features. The ultimate test was transferring learn policies to a real robot. The team evaluated success rates, identified failure modes, and compared performance to other approaches. Despite some hardware and software challenges, the robot successfully performed cloth manipulation tasks it had only practiced in simulation. The project demonstrated that with the right combination of simulation, domain randomization, and deep RL, robots can learn complex manipulation tasks entirely in simulation and transfer those skills to the real world. This opens the door to safer, faster, and more scalable robot training for a wide range of applications. Despite the successes, some limitations remain. The simulation still lacks perfect self-collision and deformation stability, and some tasks, like cloth flattening, are not yet feasible. Future work will focus on improving simulation fidelity, expanding the range of tasks, and further optimizing learning algorithms for even better real-world performance. This research has broad implications for robotics in homes, healthcare, and industry. By enabling robots to handle flexible, unpredictable materials, we move closer to practical, adaptable robotic assistance. The open-source contributions also benefit the wider research community, accelerating progress in this exciting field. This project was a collaborative effort with invaluable contributions from supervisors, lab members, and loved ones. The support, advice, and shared resources made it possible to tackle the technical and logistical challenges along the way. Such teamwork is essential in pushing the boundaries of robotics research. The results of this work were shared with the broader scientific community through a publication at the Conference on Robot Learning, CoRL, 2018. Engaging with the community helps validate findings, inspire new ideas, and foster collaborations that drive the field forward. To sum up, this project achieved several firsts: realistic cloth simulation in Pibolet, end-to-end learning from pixels, robust sim-to-real transfer, and open-source contributions. These advances set the stage for future research and practical applications in robotic manipulation of deformable objects. The journey doesn't end here. The next steps include improving simulation fidelity, tackling more complex tasks, and integrating more advanced learning algorithms. As robots become more capable of handling the unpredictable, their usefulness in everyday life will only grow. Conclusion: this project marks a significant step forward in teaching robots to manipulate deformable objects using deep reinforcement learning. By combining simulation, advanced algorithms, and careful engineering, the team has paved the way for more adaptable, capable robots. The lessons learned here will inform future research and bring us closer to a world where robots can help with the most challenging, flexible tasks.